Hello everyone. Welcome to today's live interactive session on geology and soil mechanics. So, today is the eighth week of our discussion session, and today we will be starting the shear strength of soil topic. We will be revising a bit about that, revising all the stuff that was taught in the class, and then we will solve some easy problems. Okay, some basic problems. All right. Till now we have studied many things from consolidation to seepage, to index properties to soil classification, right? In situ stresses and many other things, right? Slowly we are nearing the end of this course. So in today's session we will be starting the shear strength chapter. Okay, and after today, the next session will be on Monday, the coming Monday, that is on the what is the date? Let me check once. Yeah, on the 24th, that will be the ninth week discussion session. All right, let us slowly start our session. Okay, let me see what's there in the slide. Just a second. Just a second. Yeah. Yeah. So, what is shear strength of soil? So, the shear strength of soil is the inertial resistance per unit area that the soil mass can offer to resist failure and sliding along any plane inside it. So, say you have a soil mass, right? And say there are some external forces due to which there is a tendency for the soil mass to slide. Okay, there is a tendency for the soil mass to slide over any plane. Over any plane. Okay, over any plane, there is tendency for the soil mass to slide. Now, the internal resistance of the soil to this resist this sliding is known as the shear strength of the soil. Okay, so yeah, so that is nothing but the shear strength of the soil. Now, next is the Moore-Coulomb failure criteria. So, what is the Moore-Coulomb failure criteria? Material fails because of a critical combination of normal and shear stress, and not from either maximum normal or shear stress. So, you have a soil mass. So, in the soil mass, in any plane on the soil mass, you have both normal stresses acting as well as shear stresses acting. Now, the soil fails, that is, the soil is unable to take any more load and it shears off and it slides off along that plane when there is a critical combination of the normal stress on that plane as well as the shear stress. Okay, so soil does not fail whenever soil doesn't fail when we have neither when we have maximum normal stress or nor when we have maximum shear stress. It fails when you have a critical combination of both normal and shear stress. Okay, when it has a critical combination of both normal and shear stress. Okay, it doesn't fail when it has uh, maximum normal or shear stress. Okay, understood, right? So you might think that someone might think that maybe it fails when it has the maximum normal stress, or some other person might think that the soil fails when it is maximum shear stress, but this doesn't happen. It fails when it is a critical combination, some value of normal stress, some value of shear stress. Okay, some critical combination, in only that case the uh, soil fails. Okay, that is the shear stress is a function of the stress. Okay, both normal stress and the shear stress. Okay, so if you want to plot the shear stress with the stress with the stresses, so we'll get envelopes a curved envelope something like this. Okay, a curved envelope something like this. Now this is called the failure envelope. Now, if the soil cannot have a stress over this, that means in these stress values of the stresses, in these values of the combination of the shear stress and the normal stress, the soil will fail. Okay, but if the soil has a combination of shear and normal stress that plots below that line, then the soil will not fail. Okay, or above on the line, the soil will not fail. But the soil cannot have a stress state. Okay, any point, any plane cannot have a stress state there where there is a combination of shear stress and normal stress that plots above that line. Because if it plots, it cannot plot above it because this is the capacity of the soil. Okay, so we cannot have something more than the capacity. Okay, okay. Now, yeah. So you can see this is the failure value. This is at a curved. Okay, this is non-linear, not linear. Alright, this is non-linear. Now the non-linear failure criteria was then modified using the Coulomb theory as a linear function of the normal stress. Now, what was the Coulomb theory? Coulomb theory, if you can recall from your basic physics, so if you have an inclined plane, okay, right angle alpha, then you have a what you have a sliding block, the weight is acting downwards, you have a force acting this way, you have the frictional force resisting this is the normal force that is acting, a frictional force that is resisting the sliding, all those things. If you can recall, uh, you will say that the frictional force is nothing but what? The frictional resistance. The frictional resistance is nothing but the normal force sine tan of the angle of repose. Okay, tan of the angle of repose. Okay, so this was the concept there. Okay, Coulomb's theory. So what we did, so what was done was something. So this theory was used to make something to propose something which is analogous to that failure Coulomb theory. Okay, so where my shear strength, okay, the shear stress at failure tau f is a linear function of the normal stress. So this is my normal stress. Okay, sigma tan phi, where phi is my angle of internal friction. And what is C? C is nothing but the cohesion of the soil. Okay, so my shear strength or the shear stress at failure was expressed as tau f is equal to C plus sigma tan phi, where C is the cohesion and sigma is the normal stress and phi is the angle of internal friction. Okay, so this is how the things were expressed. Now this particular equation is called the Moore-Coulomb failure criteria. Okay, this is called the Moore-Coulomb failure criteria. So the soil reaches a failure share or the failure strength or failure stress when we have a critical so we'll see that down here. Okay, so so here you can see you have the shear stress, you have a normal stress. Now now it was seen that actually it is more appropriate that we represent these terms in in terms of represent these values in terms of effective stress values, as we have seen previously that effective stress is what that defines the actual uh, grain to grain contact stresses, right? The grain to grain contact stresses. So the shear strength or the shear stress failure was represented in terms of the effective values, that is the C prime plus sigma prime tan phi prime. Okay, the prime means the effective values, effective stress values. Okay, so here you can see we can plot the shear stress and the normal effective normal stress. So you can see we'll get a straight line, something like this. This is nothing but our Moore Coulomb failure criteria. This straight line, so this makes an intercept of C prime here, which is nothing but the cohesion. Okay, the slope of the line is 5 prime, nothing but the effective internal angle of internal friction. Okay, so now any stress combination or any shear stress combination tau and sigma prime which plots here say at point A means the soil is not on the verge of failure. Okay, it is safe. The soil will not fail. Okay, in this stress combination, the soil is able to resist the external loads. Okay, at point A. Now at point B, it means it is just at the verge of failure, but my my internal resistance is enough, just enough to resist the failure of the soil. But we cannot have this asset C because it's higher than the resisting capacity of the soil. Okay, right? So this is how it is. Okay, and C prime for sand and inorganic silt is generally 0. Okay, the equation for sand and inorganic silt is 0. Okay. Next we have the Mohr circle. So this Mohr circle you must have studied in your basic solid mechanics course or mechanics of materials or whatever you call it in that course, right? This is a Mohr circle. So similarly, what we can do for any stress state. So any stress state we can represent in terms of a Mohr circle, right? Any stress state we can represent in terms of a Mohr circle. So the stress state in a soil mass can also be represented in terms of with the help of a Mohr circle, right? So say we have a soil element. Okay, in a soil mass we have this rectangular element. So the horizontal principal stresses are, you can see the minor principal stresses are sigma 3 prime. These are the effective values. Effective minor principal stress sigma 3 prime, and you have the effective major principal stress sigma 1 prime. Okay, and EF is nothing but our failure plane. Say EF is nothing but the failure plane which is inclined at an angle theta with the horizontal. Okay, it is inclined at an angle theta with the horizontal. So when we want to plot this stress state, so this is a stress state, right? So this whole thing is a stress state. Okay, this whole thing is a stress state. So when you want to plot this stress state in terms of a Mohr circle, how do you do? So you have shear stress in the y-axis, normal stress in the x-axis. So first what we do, first we have the any angle which is there on my soil element that is transferred as is a angle x on the 2D plane transfers as to angle twice x on the Mohr circle, right? So here you can see, so with the horizon, so this is the major principal plane, so sigma 1, so we plot sigma 1 here, right? We plot sigma 1 here. Now you can see this is our minor principal plane, so minor principal plane makes an angle 90 with the horizontal. So in term with the, so when we plot it in the Mohr circle, it will make 180. So 180 degree. So this is 180 degree. You can see sigma 3 here. Okay, so sigma 1, sigma 3. So now what we can do, we can draw the circle. Okay, when we, if we know sigma 1 and sigma 3, we can know the radius and then we can draw the circle. We know the circumference, obviously we know the radius, we can draw the complete the Mohr circle. Now this is our failure plane. This failure plane makes an angle theta with the horizontal. So obviously in the what to say, in the Mohr circle it will make a angle twice theta from the center. So here angle twice theta, you can say this point is nothing but our this failure plane. This point D represents our failure plane. Okay, this plane represents our failure plane. Now since this is our failure plane, so if you want to draw, if we draw a tangent to that point, if you draw a tangent to that point, that tangent will be nothing but the Mohr Coulomb failure envelope, right? So since D represents the point D represents the failure plane, a tangent drawn to that point will be the failure envelope. Okay, mode Coulomb failure envelope. Okay, and what is the equation of this tangent? Is nothing but this. Okay, the slope of this line, the slope of this line will be nothing but phi dash, right? The intercept will be C prime, right? Okay, right. So now say you have the one more soil mass where you have higher, so we you have more higher values of say what to say principal structure. So what will happen? The similar thing we can plot a bigger more column bigger what to say bigger circle. Okay, now say you have higher sigma 3. Okay, higher sigma 3, then you will have higher sigma 1. Okay, we'll have a bigger circle, but this circle will also intersect may be it's also meet the mode column failure envelope. Okay, so at this point also this line will be a tangent. Okay, this one. Okay, okay, so this is nothing but the circle. Inclination of the plane of failure caused by shear. Okay, so what is the inclination of this? So so this theta. Okay, this theta we are trying to represent in terms of the angle of internal friction. Okay, so AB is the major principal plane. Okay, so small AB. So this AB is the major principal plane. CD, yeah, CD or AB, right? So these are the major principal planes. So this in the Mohr circle is nothing but this AB. Okay, and AD is the failure plane EF. So this is EF, the failure plane, and this is nothing but the, as I said, discussed previously also. So this is my failure plane on the Mohr column. Angle BAD. Okay, so this angle is nothing but twice theta. Okay, this angle is nothing but twice theta, which is equal to. So if we use the rules of geometry and trigonometry, we'll find you can derive that angle twice theta is nothing but 90 plus 5. 90 plus 5 prime. Okay, 90 plus 5 prime, or theta is nothing but 45 plus 5 by 2. Okay, so the inclination of the failure plane is nothing but 45 plus 5 by 2 degrees. Okay. Just a second. Okay, now these two relations that I have written, and these are very important. So we won't derive it now. Okay, right. So you must know that how these are derived. Okay, these are given in textbooks, and I think these were discussed in the class also. So these two relations, okay, or this one relation, the one form or the other form, written in two different forms. These are very important. Okay, you should remember. So this relates the major and minor principal stresses to the two shear strength parameters, that is our C and phi. So it relates the major and minor principal stresses to my two shear strength parameters C and phi. Okay, so sigma 1 prime is equal to sigma 3 prime into 1 plus sin phi dash by 1 minus sin phi dash plus 2ic phi cos 2ic prime into cos phi by 1 minus sin phi dash. You can also write this as sigma 1 prime equal to sigma 3 prime 10 square 45 plus 5 by 2 plus 2ic 10 45 plus Okay, so these two relations are very important. So what does it do? It relates the principal stresses to the C and phi. Okay, the C and phi. Okay, okay. Or you can write effective principal stresses to C prime and phi prime, or the principal stresses to C and phi. Okay, any which ways you want to write. Okay. Now let us come to the direct shear test. So direct shear test is a very simple test which is performed to find out the shear strength parameters of mostly granular kind of soil, so sandy soil, okay, sandy or gravel soils, okay. It is done to find out the uh, shear strength parameter, that is C and phi, okay, C and phi. It is done using the direct shear test. So in direct shear test, we have this box. This box has two halves, the upper half and the lower half. So what we do is that we fill our soil sample in the box. Is fill the soil sample in the box, okay, and we have to pour a stone so that water drains out, okay, tell us the water to drains out, okay, drain out, okay. And we have this shear box. In the shear box we put the sample, we put the shear, put the sandwich it between the porous stones, and then what we do, we apply a normal force in the top, okay, we apply a normal force, and then we apply normal force, and then we shear the box, okay, shear the two boxes. So uh you have the how to actually, yeah, so you have the lower part and you have the upper part, okay. So you shear the two, so soil is filled inside the box, so you shear the boxes about upper half and lower half, okay, you shear them, okay, and then you note down the, you plot the shear stress versus the your shear stress versus the strain values, okay, shear stress versus the your loading versus the strain values, okay, that will note down. So we'll see that how we can do. So specimen, so generally the specimen is generally square or square. This box is generally square, it may be circular also, okay, direct shear box, okay. General size of the specimen is 51 mm into 51 mm by 25 mm, or if you have a large box then you have 102 mm, 102 mm into 25 mm. A shear force is applied by moving one half of the box relative to other, and the stress can be either strain control or stress control. So strain control means you are moving the box, okay, you are controlling the strain rate, the movement rate of the box, okay, that you are controlling. And stress control means you are controlling the uh, force that you are applying to move the box, that you are controlling, okay. So you can be strain control or it can be stress control, okay. Okay. So what we do, we have some normal force, okay, we apply some normal force and we apply the shearing stress. So when we apply the shear stress, you will get some shear stress versus uh, strain curve like this, okay. It might be like this or like this, or it might be like this, some curve you will get. So this is for one normal stress, okay, normal stress one. So again for another normal stress you will get similar curve, you will increase the normal stress, you will get similar curve. So from all these cards, you have to take the appropriate shear stress value, whatever you desire. So it may be the peak or the residual. It's up to you. For what you have to understand for where you are going to use that values. Okay, where you are going to use the C and phi values. Okay, that you have to use. You have to judge as an engineer. Okay, where you have to use those values, and in that in the place where there you are going to use that values, where you have to use that material, which one will get mobilized, whether it will be the peak shear stress or it will be the residual stress, and which one gets mobilized, that you have to judge. So you have to take the, so you will have normal stress 1, normal stress 2, normal stress 3 corresponding to you will have shear stress 2, shear stress 3, like this you will get some shear stresses peak or residual, whatever shear stress you will get. And then you have to plot normal versus shear stress versus normal stress. So you will get something like this. You will plot the points, then you will join the line. So from there you will take the slope, you will get the phi value, and then you will measure the intercept, you will get the c value. So like this we get the shear stress parameters from the direct shear test. Okay, you can see the videos and stuff that are available online freely. Many videos regarding this direct shear test are available. You can see them. Okay, you can see them. And if you are in your undergrads or grad school, whatever, you will be doing these tests in your soil mechanics course. Okay, soil. Okay, so as I said, you can have a curve that is like this or a curve that is like this. So when you for one test, say for normal stress 1, you plot, you will get some a curve like this. So if you have a dense sand, then you will get a curve something like this, a dotted line. Or if you loose sand, you will get a curve like this. Okay, you will get a curve like this. So for the what to say, for the dense sand, you can see, it's up to you to take which shear stress value you should take. Either you should take the peak shear strength or the ultimate or the residual shear strength. It's up to you which one to take. Okay, which one to take. So as I said, you will have for normal stress 1, you will take one shear stress value, then normal stress 2, you will take one more shear stress value, normal stress, like, and that's it. Then you will plot, then from there you can get the C and phi values. Okay. Then the question is, why strain controlled or stress control test? So why do you do a strain control test or stress control? So as I said, what do you mean by strain control test? In strain control test, you are controlling the rate at which you are sharing the box. That is the rate at which you are moving the box. Okay, moving the box about one another. That is the strain control test. And what is the stress control test? The stress control test means that you are what to say, you are controlling the force at which the force that you are applying on the box, the shear force or the shear stress that you are applying on the box, that you are controlling. So why say strain control test and stress control? So generally strain control test is preferred because if you want to attain this part of the card, okay, this part of the card, then we have to go for strain control test. So generally what happens if we go for stress control test, as soon as we get the peak strength, the material fails completely and we're not able to get this other part, the residual part. But if you go for strain control test, you are able to get the this later part. Okay, so that's why we generally prefer strain control. So what I suggest you look from your end also. You just search this answer once and see what explanation is. Okay, try to read some books and also try to find out the explanation. What is the difference between strain control test and stress control test, and why we prefer strain control test when we prefer strain control test and when we prefer stress control test. Also, this is not only just the case of this particular test, strain control test and stress control test. Uh, pertain to all kinds of tests, maybe this ultimate tensile strength test. Okay, all on all tests we can have both ways, strain control and stress control both. So please see the reason. Please just do some or your own research. Go to the books, go to the internet, and find out what is the difference between strain control test and stress control test, and when we prefer strain control and when we prefer stress control. All these things. Okay. Yeah. So here you can see the results for a direct shear test in dry sandations. Okay, so these are the points that we obtained from the that is obtained from the direct shear test. Okay, so then we draw a line through these points, approximately passing through all the points or touching the points. You see that the C is 0. Okay, the position is 0. So you have a 5, you have a 5, you have a 5, but the C is 0. Cohesion is 0. For in situ cemented sands, C is not equal to 0. Okay, this is one note that is given. Now there are some limitations of this direct shear test. There are some limitations. What are the limitations? The shearing plane may not be the weakest plane. That is, here you are forcing the soil failure about this horizontal plane, right? So you have a soil mass. Okay, so you have you have the soil mass. You are forcing the shear failure about this horizontal plane. but this plane may not be the weakest plane. Okay, this plane may not be the weakest plane. Okay, there may be some other plane on in this soil mass which may be the weakest, but you are forcing the failure along this particular horizontal plane. Okay, so this may not be the weakest plane. So obviously the shear strength or the maximum shear stress that the soil can take is the maximum shear stress that the soil is able to the weakest plane of that soil is able to take. Okay, that will define the shear strength of the soil, isn't it? But here what we are doing, we are predefining the failure plane. It is the horizontal plane. The shear stress distribution over the shear surface of the specimen is not available. So, so what else? So there are two halves, right? You as soon as you have as soon as you have started to shear specimen, you have two halves. So one half will move, other half will stay. So obviously the shear distribution in this region will not be uniform. Okay, one part it will have some more concentration of shear stress, one part will have some less concentration. So the shear stress distribution will not be uniform over the plane. Okay, not be uniform over the plane. So next test that we have, one very important test that is done to determine more accurately the shear strength parameter C and phi is our triaxial test. Okay, is our triaxial test. Okay, is our triaxial test. So in triaxial test, what we do, we generally have a cylindrical specimen. Okay, with small cylindrical specimen, the general dimensions of the specimen is 38 mm diameter and 76 mm height. Okay, L by D ratio of 2 is generally maintained. Okay, so we have a cylindrical specimen with dia 38 mm high, 76 mm. Then what we do, first apply confining pressure all throughout the confining pressure all throughout the this one specimen. Okay, we apply some confining. So say if this is the specimen, this is our cylindrical specimen. First, we apply a confining pressure. Means all in all the surfaces in all the direction throughout, we apply some pressure. That is called the confining pressure. After that, what we do, we start applying the uh, deviatory stress. This is the axial stress. We start to apply. Just we start to increase the axial load. So that is called the deviatory stress. And this application of deviatory stress, it gradually causes the failure of the sample. Okay, we will see some cracks, shear cracks developing in the sample. Okay, so this is how the triaxial test is done. We will see in detail in the next slides how this triaxial test is done. So generally so this is the old whole triaxial arrangement. Okay, so in between, first we have the soil sample. Okay, we have the soil sample. This soil sample is first enclosed in a rubber membrane. Okay, you have a rubber membrane. Okay, you have a rubber membrane where this is enclosed, where this soil specimen is enclosed. Okay, we have a rubber membrane where the soil specimen is enclosed and at the top and the bottom, we have put some porous stone. Because we have put some porous disc. Okay, we have put some porous disc so that water can easily enter or exit from the soil. So the specimen. Okay, and then what we have? Then we have water all around the sample. This water actually helps to apply the confining pressure, equal pressure all throughout the sample. Okay, this helps us to apply the confining pressure. Okay, this helps us to apply the confining pressure all throughout the sample. All right. Okay. So now next, what is generally done is that first what we do, there are mainly two valves, two drainage valves. So first in the confining stage, what we do, we keep we allow the water to fill the valve. Okay, fill the valve, and then we close the valve so that the pressure is maintained. So these close the valve so that the pressure is maintained. So that pressure, that maintained pressure actually applies this confining stress all around the soil sample. Okay, so we can control this pressure. Everything we can do. Okay, everything we can do. And later in the, so there are two stages which form the triaxial test. So first is the confining stage and second is the shearing stage. In the confining stage, what we do, the drainage valve is closed and we apply some confining pressure. Okay, confining pressure. Then what we do, then so we will come to that. Okay, so first you have the, so for now just remember that we have two stages. First stage is the first stage is our, what to say, first stage is our this confining stage, and the second stage is our shearing stage, or the first stage is called, also called the consolidation stage, and then we have the shearing stage. I will see that these terms will come clear as we discuss more. Okay, so now the triaxial test, we can have three types of triaxial test: CD test, CU test, and UU test. First, let us see what is UU test. UU test means unconsolidated undrained test. So in unconsolidated undrained test, what we do, as soon as we apply the, so first you do, first we apply the pressure, apply the confining pressure, and when we apply the confining pressure, in that at that time we keep the drainage valve closed. We keep the drainage valve closed. That means what? That means the water from the soil cannot drain out. If the water cannot from the soil cannot drain out, means that means you are not allowing consolidation to happen. So water cannot come out. So obviously there will be no volume change. That is, there will be no consolidation of the sample. Okay. So in UU test, the, so we apply some confining pressure, and then immediately in the second we start the second step. In the second stage also, when we apply the axial load, when we apply the axial load onto the sample, in that stage, in that step also, we keep the drainage valve closed. So in both the consolidation stage, we keep the drainage valve closed, as well as in the shearing stage, we keep the drainage valve closed, so that we do not allow any volume change to happen. Then what we do, then we start in the second stage, we start apply the load, and then we take the drainage. So we'll see that in detail. Then we have the CU test. In CU test means the consolidated apply equal confining pressure, and then we open the drainage valve. After opening the drainage valve, we allow the soil to consolidate. So we allow the consolidation of the soil to happen. Okay, we allow the consolidation of the soil to happen. After some days, when the consolidation is over, okay, for clays it takes some days. So after some days, when the consolidation of the soil is over, what we do, we close the drainage valve and then start applying the deviatoric load, that is the axial load. Okay, that is, we start shedding the sample after closing the drainage. And last is the CD test. In the CD test, similarly, in the first stage, we apply the confining stress, we open the drainage valve, we allow the consolidation to happen, and then when we apply the axial load in the shearing stage, in that time also we allow the drainage to happen. Okay, this load is also applied very slowly, so that no excess pore water pressures are developed. Okay, so let us see this view CU and CD test in detail a bit. Okay, not that much. You will see the stability. Okay. So this was already discussed in the class, and also it's given in detail in the book. So we'll just roughly see, okay, what these tests are. So in UU test, in unconsolidated undrained test, in the consolidation stage, my drainage valve is closed, as well as in my shearing stage, also my drainage valve is closed. That is, you are not allowing the drainage to happen. That is, no volume changes. Now, what we do, initially we apply some confining stress. Okay, so this confining stress is nothing but a sigma 3 minor principal stress, right? Minor principal, so if sigma d, we have sigma 1. So we say you apply some, initially we apply some confining stress, or the minor principal, this is equal to the confining stress. Okay, confining stress, say 1 kPa, and then you will see that the soil say fails that, so this we apply, and then you start applying the deviatoric stress or the axial load, you start applying. So you will see that the soil say fails at an axial load of 2 kPa. So what will be my sigma 1? So if you want to see, if you want to imagine, so this is my soil sample. So first you are applying the what? Sigma 3 all around. All around we are applying sigma 3, and then in the shearing state over that we are applying my sigma d also. Okay, we are applying my sigma d also. Okay, sigma d also. So what is my major principal stress? Sigma 1 is nothing but sigma 3 plus sigma d. So sigma 1 will be 3. Now say you, so first test you did, so you saw that the soil sample failed at a sigma d of 2. Now you increase the confining stress. Say you make the confining stress 2. Again you will see in UU test as the soil fails at a sigma d of 2. But now my sigma 1 is 1, 4. Again you increase it to 3. Again you will see that the sigma soil fails at the sigma d of 2. Okay. So again it will be 5. So if you want to plot the Mohr circle, you will see for first one. So sigma 1 is 3 and sigma 3 is 1. Circle will be something like this. For the second one, also you can see the radius of the circle or the diameter of the circles will remain the same. This is 4, this is 2. Okay, then next you will have thing like this, something like this, right? So if you plot a tangent to this curve, you will get a straight line like this. So from UU test, you will get that this phi is equal to 0. Okay, because you, for all the Mohr circles, you will get the same diameter. Okay, phi will get 0 and you will get some value of C from here. Okay, this is the UU test. So UU test is kind of similar to my UCS test, unconfined compressive test. Okay, in unconfined compressive test is a version of the UU test where in unconfined compressive test my sigma 3 is 0. Okay, that is the difference. Okay, my sigma 3 is 0. Okay, so if I want to plot my unconfined compressive test, it will be something like this. Okay, because my sigma 3 is 0 and it will be 2, something like this. Okay, this is for my unconfined compressive strength test. Okay, okay. So why this thing happens is there. So first, one more thing I forgot to tell mention that in the, you need to saturate the soil sample completely. Okay, you need to saturate the soil sample. So what happens when you apply the load? So the drainage valve is closed. You are not allowing any water to come out. So there is no volume change, no consolidation, nothing. So as soon as you apply the heavy load, it's gonna fail at the same load because the soil soil can take a specified load only. Now when you increase the sigma 3, the extra increase when we apply the sigma 3, the extra increase in load, it's taken by the poured water. But the soil fails at same load only, same it is 2 only because the soil can take that load itself only. It cannot take more load. The extra load that is comes from my confining stress. That load is actually taken by the poured water. Okay, that load is transferred to the pore water, and my soil is failing at the same load of 2 because it can take a specified load itself. It cannot take more load because we are not allowing drainage, you are not allowing volume change, you are not allowing consolidation. Okay. Next we have the CU test. So in CU test, what happens in the first stage? First we uh, 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 saturate the sample, we apply the confining stress. After application of the confining stress, what we do? Allow the soil to consolidate. Okay, we allow the soil to consolidate. Okay, we allow the soil to consolidate to a particular value, and then we start applying the deviated load. We apply the confining stress in the first stage, in the consolidation stage. We apply the confining stress to saturated sample, and then we allow the soil to consolidate. After the soil consolidation is over, we apply the deviatoric stress, apply the consolidation, apply the this stress to vertical, apply the deviatoric stress, and then we see at what stress it fails. So say you have sigma 3 again, sigma d, sigma 1. Okay. So say you initially have a sigma 3 of 1. Okay. Then, okay, sigma 3 of 1. We apply 1. So you increase a little bit, you increase the confining stress, you allow the soil to consolidate completely. So allow the, after the consolidation is over, you maintain a sigma 3 of 1. You maintain a sigma 3 of 1. After that, you apply the deviatoric stress of the axial load. You will see that the soil fails at say 2. Now sigma 1 is what? 2 plus 1, 3. Now next what you do, increase the what to say, increase the sigma 3. Okay, again you allow the soil to consolidate completely at that sigma 3 value. You allow the soil to consolidate completely, and then you again start increasing the sigma 3. So now sigma 3 is a 3. Now you will see the sigma d has maybe increased to 7, because as you are increasing the load, increasing the confining, the consolidating effective stress due to which the consolidation is happening. So as soon as you increase sigma 3 to from 1 to 3, and then you allow the consolidation of the soil sample to happen, the soil will consolidate more. There will be some changes in the sample, there will be volume change in the sample. So obviously it will be able to take now more load, more load. Now it will take a load of 7. So now my sigma 1 has become 10. So like this test will go. So plot the, if we plot the this curve, we will see that. So first say we'll get a curve like this, then you will get a bigger circle like this. Okay, like this. So like this the test will go. Okay, one more will come. If one more test you do 3 tests, so we'll get like this. Like this, a test will go. So after the test, what you do? You plot a common tangent to all the 3 curves. You plot a common tangent and then to take the slope. This will give you the phi, and you will have the c here. You will have the c here. And now, if you so so during the application of this deviatoric flow during the shearing stage, you are keeping the drainage valve closed because it's under in CU, under in test. So in that time when you apply the load, you will have some pore water pressures that are going to get generated. Now this pore water pressure also you can measure. Well, during the test you can measure. Now if I also make one column here and write the pore water pressures, I can get the effective values. Effective values I can get like this, effective values of the principal stresses I can get. So it will be, the circle will be, this circle will be something here, this circle will be something here, like this I will get. So I can draw one more card. Okay, one more line like this from here. This will give me the effective values. Okay, effective values of C prime and phi prime. It will give me the effective values. Okay, so these are my total values and these are my effective values. Effective values, how can we get? We can get like this. Okay, we can get like this. Get like this. Okay. Now, if the soil is normally consolidated, remember this. If normally consolidated soil, normally consolidated clay, Okay, then also my C will always come as 0. Okay, my C or C prime will come as 0 for normally consolidated soil. Okay, for normally consolidated soil, what happens? We will see that the uh, envelope passes through the origin. Okay, my C will be 0. Okay, that is for my normally consolidated soil. Normally consolidated soil. Okay, so these things we are discussing in very basic manner. Okay, in each and every thing, in each and every concept in this thing. This is very important. This is not that easy, not that superficial. Okay, you can go into depths in this. Okay, these are very conceptual. From here, we have a topic also. You have something called the critical. You have something called the critical theory also. Those things all are related to the shear strength and everything. Yeah, strength, consolidate, CS, normally consolidated, over consolidated, all these things. Okay, so this is a very vast topic, very detailed topic, and but in this level, in undergraduate level, we are discussing, you are just introducing things a bit. Okay, we are introducing all the topics, so it is very difficult to get all the things correctly, everything is very difficult. So just try to get the basic concepts of each of these tests and what are happening. Read the basic test textbooks. That will be sufficient. That will be sufficient for you. Okay, that will be sufficient for you because this shear strength topic is very important and very basic to soil mechanics, and it has a lot of depth in it. Okay, so we cannot cover a lot of depth in this particular course. Okay, that is the problem. Okay, this requires a whole more detailed discussion and everything. Okay, so just we are discussing a bit in the superficial way, but just try to take the key points and read the books and try to grasp the key point. Okay, the basic soil mechanics books and all those things, and try to grasp the key points from them. Okay. Hmm. Just a second, I'll just see something. Just clarify something. Remember. So this is for the normal. So now if you now say if we have a over consolidated soil, in the over consolidated normally consolidated clay generally have a positive pore water pressure that develops. Okay. So so sigma 1 prime will be obviously less than sigma 1, and sigma 3 prime will be less than sigma 3. But if you have over-consolidated soil, then what will happen? Then we have negative pore water pressure stress developed. Okay, that is one more case. Okay, that time if this is my original total stress mode circle, then my effective mode circle will be like this. Okay, it will increase by that pore water pressure. Okay, that is a different case. Okay, that also I suggest you go to some books and you can understand. Okay. And finally, you have the CD test. So what is the CD test? CD test is consolidated drain test. So first what we do, we apply confining stress and then we allow the soil sample to consolidate at that particular confining stress. And then after the consolidation of the soil at that level of confining stress is over, what we do is shear the soil sample by applying some deviatric stress. And while application of the deviatric stress is also what we do, we consider the drainage valve is open. We open the drainage valve, we allow the drainage to happen so that the water can drain out. And this test is actually done very, very slow. This test takes a lot of time because during the shearing stage, it is the second stage also, as you're allowing drainage, the loading has to be very slow. The loading has to be very slow so that so that the pore water pressures do not develop. The excess pore water pressures do not develop. The loading rate has to be very, very slow. Okay, the rate has to be very, very slow so that the pore water pressures do not develop. Okay, that we have to keep in mind. So that's why this CD test is a very slow test. Okay, so from CD test generally we get the effective this one only envelope only, because since the pore water pressure is zero, directly we get the effective values. So we will get the effective. Okay, and similar to the CU test, the C prime is 0 for normally consolidated clays. Okay, normally consolidated clays. Now I spoke about the unconfined compressive stress test, unconfined compressive strength test. So in unconfined compressive strength test, there is no confining stress that is there. Okay, there is no confining stress that is there, and directly what we are doing, we are sharing the sample directly. We are just sharing the like we are applying the particle, the axial load on the sample. So this part is not there. Okay, so we have sigma equal to 2IC 10 45 plus 5/2. Now, generally, this unconfined compressive strength test is it is done for clays, right? So phi is equal to 0, friction is 0, friction is 0. So we have sigma 1 is equal to 2IC. Now, what is my sigma 1? Sigma 1 is nothing but the load compressive unconfined compressive strength. Sigma 1 is nothing but the unconfined compressive strength, nothing but the 2IC. So what is my cohesion? Cohesion is nothing but the unconfined compressive strength by 2, right? Right? That I just wanted to show you. Okay. Now let us just solve the problems. These problems, easy, simple problems, so they are very fast. Yeah. So first we have compute the shearing strength. Compute the shearing strength of a soil along a horizontal plane at a depth of 5 meter in a deposit of sand having the following properties. Angle of internal friction is 38 degrees. Dry unit weight is 17.06 kilonewton per meter cube. The specific gravity of solids is 2.69. Assume groundwater table at a depth of 2.4 meter from the ground level. Also determine change in shear strength if the water table rises up to the ground level. So you have you have a horizontal plane at a depth of 5 meter. Okay. And the groundwater table is assumed at a depth of 2.4 meters. Alright, phi is 38 degrees. Now, what is the effective stress at that level? 0.4 into 17.06 plus 2.6 times 2.6 times how much? The submerged unit weight. Now, how to get the submerged unit weight? Submerged unit weight is G minus 1 by 1 plus E gamma W. So 2.69 minus 1 by 1 plus 0.546, 9.81. So this one will be, let me just check. With 10.72, or 10.7. Okay. Okay, so this one will come out as 68.82 meter square. Therefore, the shear strength, so since the sandy soil C can be considered 0, 3.76. Now, second case, if the water table rises to the ground level, then this one will be 5 into 10.7. Okay, and this E I did not show you. E is found out like this. Okay, so gamma tri here, C gamma W plus E is equal to G gamma W minus 1. So gamma tri is given 17.06. From there, you can find out this is 0.46. Okay. A given saturated clay is known to have effective strength parameters of C prime is equal to 10 kPa, 5 prime is equal to 28 degrees. A sample of this clay was brought to failure quickly so that no dissipation of the pore water could occur at failure. It was known that major principal stress was 60 kPa, minor principal effective stress was 10 kPa, pore water pressure at failure 20 kPa. Estimate the values of major principal stress and minor principal stress at failure. What was the effective normal stress on the failure plane? Okay, simple, just you have to directly use the relations. Okay, first we have a failure is 20 kPa, sigma 1 is equal to sigma 1 plus UF, and the sigma 3 is 30. Similarly, now we have the normal stress, effective stress at the failure plane. Okay, the normal effective stress at the failure plane is given by this. Right, so my 2 theta is equal to 90 plus 5 plus theta is equal to 45 plus 5 by 2, 45 plus 28 by 2 to 59 degrees. Therefore, 60 minus 10 to 23.26. Okay, so this is the effective normal stress on the failure plane. Okay. All right, and the other yeah, another results of this simple. A direct shear test carried out on a sandy clay gave the following results. Vertical load is given, a number of divisions of the probing ring dial gauge. One division is equal to 1 micrometer. It's given. Shear box is 60 by 60 mm and the probing ring constant is 20 Newton per micro mm. Determine the apparent cohesion and angle of internal friction of this soil. Okay. So we have load, probing ring reading, and then we have the shear force in ton. Okay. So this times 20 will mean in Newton. Okay. So load is 36.8, 17, 340, 73.5, 6, 20. Okay, so shear stress and normal stress. So for first one, it will be how much? Shear force 340 by 60 into 60. So 340 divided by 60 into 60 equal to 0.094 Newton per mm square. Similarly, normal stress will be how much? Load 36.8 times 9.81 divided by 60 into 60 equal to 0.1. Okay, so next 0.194, 0.3, 0.244 and 0.4. Okay, after that what you have to do, you have to plot this tau and the normal stress. Okay, you have to plot, you will get some line like this, and from there you have to take the angle phi, and you have to measure this intercept C. Okay, if you do that, you will get phi is 26.5 degrees. Let's see this question. The standard specimen of cohesionless sand was tested in triaxial compression test, and the sample failed at a deviator stress of 482 kPa. Now the cell pressure was 100 kPa under drain conditions. Okay, that is the pore water pressure is drain condition. Effective value. Find the effective angle of shearing resistance of the sand. What would be the deviator stress and the major principal stress at failure for another identical specimen of sand if it is tested under a cell pressure of 200 kPa? Let us solve. We'll use the uh, basic equation. Okay, so the deviator stress at failure is kPa. This is when my sigma c is the prime is what? 100 kPa. Okay, we have to find out the I prime. Now sigma 1 prime is sigma t prime plus 3 prime. 282 plus 100 equal to kPa. So cohesionless sand, right? So cohesionless sand means what? Means C is 0. No cohesion. So this goes out. So we have 582. So if you do this, you will get prime is 44.976. Okay. Okay, so you found out the effective angle of shearing this. And the next part, what will be the deviator stress and measure of another identical specimen? It says in the cell pressure at 200 kPa. Now the cell pressure is 200 kPa. Okay, but specimen is identical, means phi will remain the same. On 164 kilonewton per square. So deviatric stress is 964 10 per meter square or case. So this is my final answer. Okay, quite simple, isn't it? Right? So hope it is clear to you. And if you have any doubts, you are always welcome to ask anything. Yeah. Just a second. Let's see this. Two identical soil specimens were tested in a triaxial apparatus. The first specimen failed due to a weight stress of 770 kPa when the shell pressure was 200 kPa. Second specimen failed due to a weight stress of 1370 kPa and the shell pressure was 400. Determine the C and phi analytically. That means we got two equations. You can solve for two unknowns, C and phi. If the same soil is tested in direction repetition, normal test of 300 kPa, estimate the shear stress. Okay, so it's easy. First, let us build up the two equations and solve it for C and phi. Then we will come to the third part. So sigma 1 is sigma 3. Right. So sigma derivative stress is given, cell pressure is given. So cell pressure by derivative stress is nothing but sigma 1. That's my first equation. Similarly, I can have two, so I can have 2 minus 1. Again, therefore, 17, 70. So from here, we will get yes. That's clear. Now, the final part is direct shear or estimate the shear. So it is tested in direct shear test. Then what? 5. Okay. Let's look at the next problem. A CD triaxial test was conducted on a normally consolidated clay, yielding the following data. Minor principal stress given, derivative stress given, determine angle of internal friction, angle which the failure plane mixed with the major principal plane. So if I encountered the angle of internal friction, obviously I can easily encounter that. And the normal stress on the plane of the maximum shear stress, that also I can. Okay. So KPA. So CD test on normally consolidated clay. For normally consolidated clay, CD, you know the C is equal to 0. So sigma 1. Since C is 0, we don't have that part. From here we can get yes. So this is my inclination of the failure plane with the major principal plane. Okay, this is the inclination. Now normal stress. Meter square. Now, what is the shear stress? So this is the normal stress at the failure plane. Now, how to get a shear stress at the failure plane? What is 120? Now, remember that a shear stress at the failure plane is not the maximum shear stress that the soil encounters. The shear stress, remember, initially I told you, the first slide of today's class, soil fails at a critical combination of normal stress and shear stress. Neither at the max plane where the maximum shear stress is there, nor at the plane where the maximum normal stress is there. Okay, the shear stress of failure plane is this, but this shear stress is not the maximum shear stress that the soil encounters. So you want to see, so you say like this, right? So you move circle, okay, like this. Yeah. Now, okay, this is the now the this is the point. So this is the understood. This point is this, the normal stress and the shear stress at the failure plane. Now, what is the maximum shear stress? The maximum shear stress is nothing but this, the radius, this point, this point. Okay, this point. This is the maximum. So, what is the maximum if you want to see? It will be nothing but sigma 1 minus sigma 3 by 2. So, this is the maximum shear stress in that soil sample that the soil sample encounters, the soil mass encounters, not the shear stress at the failure plane. The shear stress at the failure plane is this much. Okay, always remember the plane of failure is not the plane of the maximum shear stress. Okay, okay. The plane of the maximum shear stress is this here, which is always inclined 45 degree with the horizontal. Okay, let's come to the next problem. A CU triaxial test was conducted on a soil sample with cell pressure 100 kPa. The deviator stress at failure was observed to be 60 kPa. The soil is known to have a C prime is 0, phi prime 30 degrees, and unbent CU is 0. Okay. What is that? What is the pore water pressure at failure? Okay, so let us see how to do. So first we have how much is 100 kPa. cell pressure, cavity weight stress as 60 kPa. So my sigma 1 is nothing but 100 plus 60 is 160 kPa. Now, what are the effective values? Sigma 1 minus pore water pressure. Similarly, sigma 3 prime is sigma 3 minus the pore water pressure. Let it be U. Now, sine, please remember, sine phi 100 is nothing but phi minus 1. Yes, okay. Please remember this. Also, sine effective is nothing but these all have come from the geometry or from using the trigonometry within the mode circle and all those mode circles. Okay, we are not going to the derivation, just you can remember. Okay, right? So then we can have okay. So sine 30 is half. So effective is the effective. Okay, this is given in the question. So my U comes as 70. Okay, so this is my pore water pressure at failure. Okay, just check the calculation once. Check the calculation once by yourself. Okay, so user cancel 60 260 260 minus twice U 260 minus it's fine. The effective shear strength parameters of a completely saturated clay are C prime is equal to 20 kPa, phi prime is equal to 28 degrees. A sample of this clay was tested in UU test under a cell pressure of 180 kPa and a weight stress at failure was 100 kPa. What was the value of pore pressure at failure? Okay, let's see. So effective shear strength parameters are completely saturated. Okay. Okay, so C prime is given degrees, this is kPa, right? Just a sec. You just do this a bit. I will be back in a minute. Just do this. Try to do this. Yeah. Yeah. So phi prime is 28 degrees. You have okay. So sigma 1 prime is sigma 3 prime. To 80 minus pore water pressure, we say it is U. The water pressure will come out as 161 point. That yes. Okay. So just from this equation, basic equation, you put you put consider U as the pore water pressure, and then you can deduct it. Okay, you can find it now. The results obtained from a series of CU tests on a soil gave the following results. We have CCU C prime is equal to 0, sigma CU 17 degrees, sigma prime CU 34 degrees. If a sample of this soil, if the sample of this soil was tested in a CU test under a cell pressure of 180 kPa, determine this. Okay, let us see. Let's see. Just do I see then? Okay, so C is 0, 180. 10 square 17/2 328.74. So derivative stress is sigma 1 minus sigma 3. It will be nothing but 328.74 minus 180, that is 148. Now pore water pressure at failure. Calculate in terms of effective values now. Square 45 plus 34/2. 228.74 minus u. Okay. And we have next is major principal effective stresses failure. So major principal effective stress, nothing but this. One is minor principal effective stress at failure. Compression test was conducted on a cylindrical soil sample. It failed under an axial stress of 120 kPa. The failure plane makes an angle of 50 degrees with the horizontal. Determine the cohesion and the angle of internal friction. Okay, this is also simple. UCS test values are given. Theta is equal to 50 degree to 45 plus 5/2 implies phi is equal to 10 degrees. So equal to sigma 3 10 square 55 plus 5/2 plus 2IC 5 plus 5/2 sigma 3 is 0. Since it is a UCS test, so C is sigma 1 by 210 45 plus 5/2 plus 120 by 2 into 10 45 plus 10/2. That is 50.35 kPa. Okay, 50.35 kPa. Simple, just simple. Same equation you are using again and again, again and again. That's all. Okay, same basic equation. If in an uncompromising university test, a sample of clay 100 mm long and 50 mm in dia fails under a load of 150 Newton at 10% strain, calculate the shearing resistance taking into account the effect of change in cross section. Okay, so my is 10% strain, longitudinal strain is 0.1. So area is A naught by 1 minus strain pi by 4 into 50 square by 1 minus 0.1 to come out as 21.82 centimeter square. Now UCS, that is QU, is 150 by 21.82 Newton per centimeter square, 6.87 Newton per centimeter square. So tau is C plus sigma phi. Now K, that is phi is, we can consider 0, phi you can take as 0 degrees, therefore nothing but C is nothing but what? C, yeah. Tau is equal to C, and C is nothing but QU by 2 is 6.87 by 2, right? So it is that. 34.35 kilonewton per meter square. If you convert centimeter newton per centimeter to kilonewton per meter square, it will be 34.35 kilonewton per meter square or kPa. Okay. Right. So C is Q by 2 from where? We got from that equation only, right? From this basic equation only. So phi is 0. So sigma 1 by 2, sigma 1 is nothing but Q, so Q by 2. Okay, understood, right? Now, last problem for today. Laboratory results on a soil have shown that the UCS is 120 kPa. In a triaxial test, a specimen of the soil when subjected to a chamber pressure of 40 kPa failed at an additional stress of 160 kPa. Estimate the shearing strength of the same soil along a horizontal plane at a depth of 4 meter in a deposit. The groundwater table is at a depth of 2.5 meter from the ground level. Take drive need without. Okay, so we have UCS as fraction test. This is 40 kPa. Sigma T is 160 kPa. Okay, so sigma 1 is sigma 3 10 square 45 plus 5 by 2. Do I see 10 45 plus 5 2. So for the UCS, my sigma 3 is 0, so I can write 120 is equal to 2IC 10 45 plus 5 by 2. This I can write, okay? That's market equation 1. Okay. Now next, from the triaxial sample, I can write 160 plus 40 equal to 40 sigma 3 10 square 45 plus 5 by 2 plus 2IC 10 45 plus 5 by 2. Okay, so 200 equal to 40 10 square 45 plus 5 by 2 plus 120. Okay, so this is 120 I got from 1. Okay, from here I can get 2 is equal to 10 square. Right, 200 minus 180 or 80 by 42 10 square 45 plus 5 by 2. Okay, so from here I can get y is equal to 19.47 degrees. So again, C I can get, if I put this in this equation, C I can get 120 by 210 45 plus 19.47 by 2 at 42.426 per square. Yeah. Now next is the last portion is estimate the shearing strength of the same soil along a horizontal plane at a depth of 4 meter in a deposit, and the other parameters for the ground are given. Water table depth and all those things. Unit weight is given. The C5 you got, so directly now we can find out. So 4 meters, this is 4 meters. This is water table at 2.5 meters. Gamma D is 0.7. Rate, I can get submerged. Put all the values and I will get this as 7.7 or 2.5 effective stress into 17 plus 1.5 times 10.7. Let's get see. Then today's session, we have just 3 minutes remaining. If you have any doubts, you can ask. But this was all for today. Yeah, I hope everything was clear. And if you have any doubts, you can get back to me. So thank you so much for attending today's session. The next session will be on Monday, coming Monday, that is on the 24th of March. That will be the ninth week discussion session. So if you have any doubts, we'll discuss or we'll solve some more problems in the next session. So thank you for attending. So if you have any doubts, you can stay and ask or you can leave. Okay. Thank you.